Hello, this is the lecture for Chapter 3 for Physics 1301. In this one, we're looking at motion, and particularly motion in a two-dimensional direction or on a plane. And so we'll look at a few of those ideas and try to share a few thoughts on it. So, vectors in terms of the Cartesian x and y coordinates. So basically what we're talking about here is having a direction in the x direction and a direction or distance, whatever the value, whatever the measurement is, in the y, and then combining those values together to determine the resultant. So the resultant r, which is the resulting arrow that connects the x and the y components, which of course is the hypotenuse of that right triangle, is equal to the square root of x squared plus y squared, x being the horizontal direction, y of course the vertical direction. From the graphs we can see both instantaneous and, excuse the sounds, my 3D printer is kicking in. From the graphs we can see both average and instantaneous velocity. Average is going to take, of course, the average change of rise over the average run to give us that slope, and then the time that it takes to do that will give us our velocity. But it's going to be an average velocity. It's going to be the time it went from point A to point B, and that time that it took to go from point A to point B. Now that's an important value that is handy and helpful to us in many cases, but it also is a limiting factor in college physics because we cannot calculate to the same degree the instantaneous velocity like we can if we're using the university physics with the calculus as its foundation. On the right of the screen, we see that being represented. So this particular point here is the tangent of the slope of that line. And so at that point right there, we can determine, right here, we can determine that that is the velocity at that given instant, assuming that the increment, the interval, is so small, very small increment, that we can calculate it right there. The smaller, of course, those increments, the more precision we have in terms of our answers. So in this case, the increment's very large, a lot of variance in it. This one, the increment's very small with our using calculus, and that allows us to get a much more precise answer and instantaneous velocity. I've mentioned it, I think, already in these videos, but mention it again. The e-text that goes along with this PowerPoint slide and with my lab has embedded within it many videos of example problems such as this one, where they walk you through some of the key steps in getting the solution. I do not take the time to do those videos because they're so well done and convenient to use in the e-text. So I would encourage you to take a look at problems where, like for example, this one, the motion of a model car, which started at a certain point and then had its motion go during a period of time and over a certain distance, and they make the calculations. So I'd encourage you to watch those videos. Accelerations in the plane. Acceleration is defined as the change in velocity over change in time. For my when I'm teaching this to high school level, I define acceleration as the time, the change in velocity how much you change, how fast you're going. Or in other words, how fast you change, how fast you're going. They seem to understand that. It's more than just changing your speed. It's the rate at which you're changing your velocity. And of course, velocity can also mean direction. Velocity is a vector quantity, so we need to be aware of that. But in terms of motion, we can define it that way. And so average of acceleration is delta v over delta t. And that's what we will be doing in this course. And so in terms of magnitude, it is how fast you change, how fast you're going. In terms of direction, you may not change your velocity in terms of your speed, but you change your direction. And the example I use in-person lecture is if you've ever been on a road trip and you're not the one driving, hopefully, and you fall asleep and you stay asleep, when is it typically that you wake up? If it's not just time for you to wake up, if you're interrupted, if your sleep is interrupted, it usually happens when the driver has to hit his brakes or changes lanes fairly quickly or gets off at an exit. All of those are examples of a change in velocity, either direction or speed. That is acceleration. Acceleration is what we feel. Constant velocity we don't really feel unless it's the vibrations of the movement, but in terms of our body sensing we're in accelerating, it doesn't experience that. So that is something to make note of. Projectile motion, again, we're talking about an object being projectile. So here's a football or baseball, some object being thrown. It has a starting velocity here, and it goes in that direction. At the top, we know that its acceleration of y is negative g, and as it comes down, it's encountering negative g at all times during this. But it is, and negative is just referring to the direction, 9.8. But as the object is going up, it's slowing down at g. When it comes down, it's speeding up at g. And so this text identifies that as the negative direction, and I've seen some texts that refer to the vertical being negative because you're slowing down as you go up. That's fine as long as you're consistent with using that all the time in both your velocities and your accelerations. In this initial velocity, we could break that down into units. If we knew the angle, we could break it down into the x and y components. If we knew one of the components, if we knew both the components, we could find the angle at which it was initially shot at. We can know that without air resistance, that the velocity that it takes off at is the same velocity it's going to be when it hits the ground. So a few points about trajectory. We should note that the x component and the y component are independent of each other and do not impact the speed of one another. This is a concept that is sometimes difficult for some to accept. I do this demonstration in my classroom and have one ball gets dropped straight down and the other one is shot out simultaneously, and you see that the rate of fall is essentially the same. They both hit the ground at the same time, and students will look at that and be fairly accepting of it. And then I'll ask them the question, what if we took a rifle and we aimed a rifle horizontally and shot a bullet, and at the same time you dropped a bullet from the same height as the chamber? Which of those bullets, the shot one or the dropped one, will hit the ground first? The vast majority of people will say that the drop bullet will hit first. And neglecting air resistance, they will hit at the same time, because the horizontal speed has nothing to do with the vertical drop. All objects fall 4.9 meters in a second when neglecting air resistance. So if I'm on a tower 4.9 meters high and I shoot a bullet horizontally and I drop a bullet, both are going to hit the ground after a second. The X and Y are independent of each other. A neat video that you might want to watch is called The Monkey and the Hunter. MIT and Harvard both have very good videos with this, and it shows a simulated scenario of the monkey and the hunter, where the monkey is hanging from a electromagnet across the stage, and it's a ping pong cannon or a tennis ball cannon shooting the projectile towards the monkey. They aim directly at the monkey, and as soon as the projectile leaves the cannon, the monkey is released. And in slow motion camera, you can see the ball hit the monkey right in the chest. And this again seems counterintuitive because the monkey's falling, but the projectile falls at a rate of 4.9 meters per second. Falls 4.9 meters in a second, and the monkey falls 4.9 meters in a second, and they still hit each other. So you might want to take a look at that video, which is easily found with a search. All right, so again, this is showing that, and we'll end with this. When that projectile is initially launched, it has a certain velocity horizontally, very large velocity vertically. And of course, with these two vectors, this would indicate that the ball or object is being projected at less than 45 degrees. Otherwise, these two would be equal if it was 45 degrees. The maximum range is without air resistance is 45 degrees. With air resistance, it's 44 degrees to get maximum range. Notice in the second one, the horizontal stays the same in all the cases. It's only the vertical that's decreasing as the ball goes up, and at the top it's 0, and then it becomes negative in terms of its direction. So projectile motion, look at some of the examples that are done in the text, and if you haven't been out of your trig classes in a while, or advanced math classes in a while, you should be fine with the math at this level.